Hello, Junho. I think Alexander
Hi.
Borisovich will join soon. He's trying to log into to the hotel network. It's a little bit tricky. So let us wait for him. Wait for him for a little while.
Okay.
Alexander Borisovich is trying to log in to the internet. Just a moment, I'll try to send Alexander Borisovich this invitation to some other mail.
Добрый день.
То есть как ты смог преодолеть все эти трудности, Саша, скажи, пожалуйста.
Ну, я просто, когда ты мне послал на мою другую почту, я открыл письмо. Дело в том, что моя почта на Mail.ru здесь просто почему-то вообще не грузится, в принципе.
Но она блокирует, они тут Яндекс иногда, скажем, блокируют. У меня тоже не всегда Яндекс открывается. В Пекине у меня половину времени Яндекс открывается только облегченная версия почты, где ужасно совершенно ничего не видно. Вот, а тут все
Ну, в том-то и
работает.
дело. Я не знаю, нет, тут Mail.ru, он вообще странно себя ведет. В Пекине он как раз нормально открывается. Ему,
Видишь, тут
по-моему, памяти
наоборот.
там не хватает, что ли, я не понимаю, в чем там дело. Но
Ну да.
здесь вот он вообще он не хочет открываться в принципе. Там
Значит,
что-то
такие.
тормозит, то ли Касперский. Я сначала Касперскому не нравилось долго, что тут какие-то сертификаты не те у самого отеля.
Ну, конечно.
Может быть, в общем, то есть, короче, какой-то бардак, я не понимаю. То есть тут, по-моему, наоборот, слишком много свободы, видимо, в гостинице интернетной, потому что я Zoom включил без проблем. Зато перестала грузиться наша почта. То есть,
Ну,
как
так
бы
всегда.
я перестал понимать вообще, что происходит. В Пекине наоборот, почта прекрасно грузится, когда нет никакого VPN. Но Яндекс не грузится в принципе, да. Это немного... В общем, ладно.
Окей. Ну, окей.
Да, давай начнем.
I think, Саша, давай ты сейчас будешь представлять, потому что это ваша совместная работа, и ты имеешь полное право сегодня быть ведущим. Я буду слушателем.
Хорошо.
Угу.
Okay. Okay, let's start today's seminar. Today is the talk by Jungho Guo. It's our PhD student from Peking University. And he will talk about our joint work, about normal forms of ordinary differential operators. And about 1 year ago, I made 2 talks about that. But now we have something new to show. Namely, there are more examples in high rank are calculated. Moreover, the work was finished, and it appeared in July in archive. And so it's time to refresh this material for everybody. And also I want to give him an opportunity to train his ability to make a talk. So Junho, please, you can start now.
Okay. Can you hear me?
Yes.
Okay. Then let's start. This talk is based on the normal forms for ordinary differential operators. First, let's give the definition of DN sim. Let K be a field of characteristic 0, and R hat be the rings of varieties x1 to xn. Consider the K vector space M is equal to R hat partial 1 to partial n. Here as the formal power series, and here AK belongs to R and K belongs to n power n. Let V here be the discrete variation defined by the unique maximum M x1 to xn of R, and denoted the order the K is equal to K1 plus 2 Kn. Then here we define the order of P is equal to the supreme of K minus V in the value of AK. Here, and here we define the DN sim to be all the operators in M such that the order is not comes to infinity. And let's introduce the properties of DN sim. First, DN sim is a ring with the natural operations, multiplications, sum from the DN. And obviously, the DN is the subring of DN sim. Here, DN is the ring constructed by the X and partial, but here the DN, the partial cannot come to the infinity order. And here DN can be some power series that partial comes to the infinity, but the order is less than the infinity. Here R hat has a natural construction of left DN sim model, which extends its natural structure of the left DN model. Here DN sim is, sorry.
The order is the difference between the powers of X and powers of operators, right? Order. Can you?
You mean the difference in DN and the DN sim?
No. What is order? Order of an operator. Can you show me again this definition?
The order is here.
Yeah, it's just difference between the power of partial derivative and the power of X, more or less.
Yes.
Yeah, that's just what I said. Thanks. Just I tried to check if I remember this correctly or not.
Okay.
Please go on.
Okay, here DN sim is a suitable universum that contains many useful objects. For example, operators from DM can be realized and arbitrary continuous endomorphisms of K algebra of hat. And here we can define the Dirac delta function, the operators of integrations, differential operators. For example, we can define this DN P alpha is the formal power series that can written in this form. And here, the operators act on the functions can be just shift the functions f into fx1 to xn to fx1 add with fn u1 and xn add with un. And especially here, if we assume that u1 and un to 0, then we'll get the delta functions. And this is the example.
What is star again? Don't quite understand. What is this?
The star is shows that the u must be written at the left hand side of partial. In the series here, u must be written at the left hand side of partial. Okay. The notations. Sorry.
just a convention, notation for
Mhm.
Okay. Here we assume that F is the DN sim modeled by the maximal idea multiplied with DN sim, that it's isomorphic to the ring constructed only by partial 1 to partial k. This is a right DN sim model. And there's a generalized Schur theorem that if we assume P1 to Pn be the commutative operators with order Pi is equal to k and all for all I, and assume the model of the ring is case. Okay. Here we to say that this is the height symbol of P1, and this is the height symbol of Pn. So it is regular that if this comes into D1, if we call it as here is Dn, cannot and okay. How to deal into this?
That was the called principal symbol, right?
Yes.
not principle, but highest symbol.
Yeah. The height symbol is come
What's the
from.
difference?
How to delete this one?
What's the difference then?
Because here for any operators P1, for example, P1 can be written as fx partial. For example, in one case there can be order P1.
So highest means highest with respect to the order.
Yes, yes. This one we call it not the regular, but if the fx comes into a constant, maybe for example in k, then we call it as the regular. So here we assume that all the operators are regular. Then we can we say that the all here then we say the ring K sigma P1 sigma Pn is finally generated and free. Okay.
Just an assumption, because it's a generic theorem.
Sorry.
So we assume that this model is finally generated and free, and the ring here is taken over, generated by this highest symbol. We now in a situation of Robertian dimensions and variables.
Yeah.
And
okay.
then yeah, because okay, don't hurry, just explain it more carefully.
Yes. Okay. Then we assume that sigma P1 sigma Pn are regular, and here the model of F of ring K sigma P1 sigma Pn is finally generated and free. Then there exists an invertible operators S belongs to Dn sim such that with the order of S is equal to 0, such that the S inverse partial I k square S is equal to Pi. So that we can. This is very powerful.
I don't understand.
Sorry?
Do you assume that F is isomorphic? So you take F, which is just the quotient of this very large ring, by some ideal,
Yes.
right?
Yes.
By some right ideal. So it's actually
Yes.
right model. And then you say that the
You
model.
mean why is of isomorphism?
Well, since you have standard things on both on the left side, it's not a problem. What really disturbs me is that you take the module F of the ring. This is not module of the ring of this sort. It's module of I don't know what it means. It's quotient. It's quotient. It's quotient. Well, it's right module over the original ring, for anything I know.
Yeah.
Yes,
But you say it's module of the ring with a very strange notation. So I don't quite understand the notation, the assumption you make.
Here M is the maximum idea constructed by.
Yeah, that's clear. That's clear. So far, so good. I have no problem with this. I have problem with understanding what it means that the module, which is actually just the ring of differential operators with constant coefficients, right? Nothing else. Why does it mean that? What does it mean that this module is module of the ring, that the F, which is just the ring of constant value of constant coefficients in differential operators? What does it mean that this ring is module of ring something different?
This is module of the ideal.
No. He just asks Jean-Paul, why? What does this mean that that we consider this model of the ring generated by the symbols?
Yeah, something very natural. It's naturally a ring over. It's naturally a module or a right module over DSIM.
Yes, it's originally the DNC module.
Yeah, but then this ring which you consider generated by symbols is not a subring inside this, so you cannot even restrict it there. So much as I can understand. So what?
But in fact, yeah. In fact, it is a subring. This is a subring of DN hat sim.
So how happens? So what do we call symbol? In usual theory of differential operators, symbol is actually a function.
Yeah.
A function of two n variables. Here you have so symbol is function is symbol. They constitute a commutative algebra.
Can you write down the definition of a symbol? Sigma of P.
Because it's not standard symbol.
No, it's highest symbol.
Standard?
Highest symbol.
Okay, that's precisely what made me.
Yeah. I hope.
Let me write as this F order of P. If Fp is equal to F order of P. And if
F order, P order, then the order of this term is equal to 0. If F order of what?
No. This you should probably accept this about symbol, the first slide, because when you introduce a ring, DN hat sim, you could also introduce the notion of highest symbol.
Did you? I don't remember you introduced this.
He didn't. He didn't. Yeah.
Yes, I didn't.
Yeah. And just write it on the slide.
Yes.
It's just an infinite sum, but of homogeneous components.
So it's interesting. For anything I understand, symbol should be in your sense the infinite sum in general of components with constant difference between the powers of variables and the powers of partial differential operators. For anything I understand.
And now I hope he will reproduce the definition. Wait.
If here we write P1 is into this form, and then we to infinity, and
it's somehow. So okay, this is some kind
sigma,
of.
Sigma means the highest coefficient of.
This notation is really misleading, I would say, but okay. So far,
it's just a sum. It's just a sum. Just write the sum of all monomials with, as you said, with a fixed difference between K and the evaluation.
Yeah.
The difference must be equal to the order of
the order. That's what I understood.
Yes, the K1 and
Yes.
with
So just take all the coefficients of these monomials. You just ignore all the partial derivatives.
No. The derivatives also are here.
So you just take the part with the top degree difference.
Yes.
Okay, let's now understand. But now the question is how you define the action of symbols on this quotient space, because symbols have because do they constitute subalgebra?
The symbols constructed by the varieties.
Okay, I mean, so you take these symbols, they constitute subalgebra, right?
Yeah.
Right?
Yes.
And then you just
it
take.
can be the D1 DN symbols, DN sim models here.
So somehow
the operators on the symbols can just
symbols of
view
operators,
as
symbols of any n-tuple of operators constitute a subalgebra. Is this algebra commutative? Symbols, if you take highest symbols, is this algebra commutative?
Yes, you can view as. Yeah,
I see. So if you take highest symbols and take the algebra constituted composed of these highest symbols of n-tuple of commuting operators, and these highest symbols, well, commute par excellence, as they say in French, right?
Yes.
Okay. Now it started making sense.
Yeah.
And then you assume that this algebra, when you restrict this model structure to this subalgebra, is actually gives this find the generator free. It's a pretty, let's say, pretty damn hard condition to check. But okay, at least it makes sense now. Okay, thanks.
Yeah. It's some condition which appeared usually on all quantum integrable systems, because all reasonable quantum integrable systems appear to have this condition. This is the point. And you will see that
I have no objection about this condition. Just
yes.
matter that is very hard to check in general. But okay.
Yeah. Well. Okay. It's a good question for discussion. That is right.
Okay, let's continue. Here we fix k is an integer number and fix case primitive roots of unity psi key. For any I in of integer, we can define the operators AKIQ and the integral Q square. The AKIQ is just some special operators. It is always of order 0. Such and additionally, AKIQ K square is equal to 1. And the integral Q square is just the right inverse of partial Q. That the partial Q multiplied with integral Q is equal to 1, but the integral Q multiplied with partial Q, there will be additional delta functions. We can write here. These are special operators. And here integral Q multiplied with partial Q is equal to 1 minus delta Q. And the delta Q is just the function we introduced before, just let the alpha equal to 0 there. And here the partial Q multiplied with integral of Q is equal to 1. And here, so that the integral of Q is just the right inverse of partial Q. Okay. Okay. The next, the centralization theorem. Assume that the Q is commutative with the partial Q k square, and for q from 1 to n, and with q is in the Dn thing, then q should be constructed in the such form. It can be written as the sum of all multiplications of akj1 to akjn. Here, all coefficients are polynomials in partial q and integral of q. So, with constant coefficients and the degree of the partial q is less than no more than the order of q, and the degree of integral of q is less than k minus 1. We can just view this in the instruction of q. We can see that if q commutes with partial q squares, then there doesn't exist x here, x1 to xn here. Just construction of partial q and integral of q, and the integral of q cannot be too much of them. The degree must less than the k minus 1. So the sum from the minus order is finite. Okay, then let's be the subset of Dn thing is a commutative ring containing n operators p1 to pn, satisfying the condition of the generalized Schur theorem, just here. Then we will call that the B prime is equal to the SB. S inverse is the normal form of B respect to P1 to Pn. Here is just we commute, just use this theorem to conjugate one elements into partial Q square, then all the other things will be all conjugates, then the B prime is called the normal form. Okay, let's now consider the generalized Schur theorem for n is equal to 1 cases. If n is equal to 1, we can the generalized Schur theorem automatically satisfies any regular operators for P in D1 thing. And for example, we can view all them as the highest coefficient to be constant 1. So if the highest coefficient becomes 1, so we call them as monic operators. So here we can view P is equal to S partial Q S inverse for some S. Now we can rewrite the Schur theory as for given Q in D1 thing, and assume that Q commutes with partial K, then Q is in the such form. Here, Cm C minus 1 and C minus K add with 1 are also the constant not containing X. And here we should notice that also the integrals is just a finite sum, not no more than K. And here additionally the minus coefficient, the coefficients of integral should satisfy the additional condition that the sum should be equal to 0. This sum, this psi is just the K primitive roots of the unity.
Can you just recall what is K tilde in this notation? It's one
sorry. K tilde is just the ring contains the primitive root.
So when you just add the primitive roots of unity?
Yes.
So why don't you assume that you have, well, algebraically closed, just to avoid all these difficulties? Is it possible, Sasha? If we just assume that we work over complex coefficients, which is perfect for my, well.
Yeah, the very easy explanation is that we apply this construction to parameterize the moduli space of torsion-free shapes. And in fact, this construction sees the points, the points. So, for example, if the moduli space have points defined over smaller fields, so we can consider here any field of any characteristic.
Okay, if we're not
Then,
trying to reach the maximal generality, can we just work over complex?
Yes, of course. Yes, of course we can. Yes, of course we can. But the advantage of this construction is that it fills any extension of a field. So it's functorial, and if you want to say more about the residue field of points of the moduli space, say if you want to study moduli space of sheaves over curves defined over the rational numbers, say, yeah, then you can do it as well, and it is and this is very nice for possible arithmetic applications. For example, if you want to study some questions on arithmetic, so
Okay, you have some really an algebraist. For me, curves over rational numbers, it looks like some abomination.
But in fact, we tried to apply with other students. For example, with Pavel, who is here, or with Junhu also, we tried to solve certain questions about the existence of operators defined over the field of rational numbers. It's quite non-trivial.
I understand.
Yes, so these questions appear also some.
When you artificially restrict somehow you try to move using only, putting both legs in one trouser. Yeah.
Yes. But so since you are right. But you're right. Since I am an algebraist, I always try to do everything in the full generality if I can, because usually it costs not much, but it gives many.
But it makes the whole thing look a little bit technical. Okay.
Yes. You're right. But nevertheless, the construction feels the extension of fields. And this is a good question, by the way, very good question, because I think many people will ask you about this. Why we take the extension?
Extension, I see.
Yeah.
Okay, so I actually kind of training Junhu to answer this question.
Yes.
Okay. I'll take the credits later.
Okay.
Thank you.
Continue.
Yes, if consider K as the algebraically closed field, then this expression will be much easier. But if only consider K tilde as a field extension that containing the primitive root, we can consider more interesting questions. Okay, next. Also, we can view the centralized. We can use another way to view the centralizers. Here, there is an isomorphism C partial Q. The centralizer is isomorphic to the matrix constructing on the ring KDQ. And here the normal form is not uniquely defined, but up to the conjugation with invertible S in D1C from the centralizer. Because the S is not unique, so we can use another S to conjugate. But after choosing the different S can be conjugated by the S in centralizer. Also, the S is here with order S is equal to 0. The bicentralizer theorem, such as is a polynomial of restricted degree. Any such operators is given by a lower triangular matrix with constant coefficients via the isomorphism from the claim above. Normal forms of B appear to be a very effective tools for the description of moduli space of spectral sheaves. Okay, next. Consider the
spectral sheaves. Did they appear before? Spectral sheaves. You are going to introduce spectral sheaves later, judging by the below. So MQ, just don't remember this notation. MQ, what was this?
Oh, sorry, which one?
But what is MQ? Is matrix?
Matrix of size Q
And DQ?
on the ring K of DQ.
D is what?
D is just the symbol that takes the place of partial.
Because we wrote sigma, and this is you used to write sigma of P, sigma of in the Schur theorem, and this is what is Q?
Where is Q?
I don't understand what's the difference between this DQ and this DQ.
This DQ is just the DQ is just a symbol to replace the place of partial Q, because later we will in written the D of we will set the coefficients of the partial comes to the coefficients of D of Q, and the D just takes the place of partial as the ring here. We construct a new ring here, just that the D and the DQ/DR is equal. If we written here D is sorry, let me rewrite it. Here if we write dr here is equal to partial r if r is greater than no less than 0 and equal to integral of r minus r if r is less than 0. Then we can matrix the things here to we can set the morphism from this place to this place. Just makes the coefficients here comes to the coefficients of D here. We will transfer this D somehow into all the terms only with DQ, not constructed only in DQ, but no other terms in the items not divided by Q here. We can see the specific construction in the next pages.
But actually, roughly speaking, D capital is just a new symbol here. Because that's the claim is that we have an isomorphism of rings. One ring is just a centralizer of partial power Q. And D had symmetry, the right, and another ring is just a matrix ring, always a ring of polynomials in one variable.
Yeah, but the way you describe this, you denote this variable, means something, suggests.
But yes, later he tried to explain that later we'll use this capital D as a formal variable of the differentiation partial and of integration if it comes with a -1 power, say. But here you can just consider it as a formal variable.
Okay. Now let's consider the skew polynomial ring R is equal to this one. And here the sigma just shifts the operators. The last one comes to the first and all the others shift to the later place. And define the right quotient ring B as the S defined by this multiple sets dk. And here the B, we can say that B is isomorphic to this ring and is constructed by the sum of PL, DL, and P is the vector of K items, and is also isomorphic to K of A1, D, and D minus. And here the D minus act on A is just the the sigma of A to D1 of the multiply with D1. And here we can say the centralizer of B, if denoted as C of B, we know that the C of B is isomorphic to the K tilde, K tilde, D K and D minus K. So, and this can obviously just the subring of B, and just when we can view as B is the ring over C of partial K. And we have the isomorphisms here. The isomorphism is induced by this phi, and the phi just maps all the vectors into this diagonal matrix and maps the operators D into this form. And here we, yes, we have introduced before that this D is partial in C of B, and the D minus is integral. And here phi of D becomes this matrix. So after this phi, we can just map the centralizer of partial K becomes the matrix ring here. Yeah.
Psi of B doesn't quite understand the formula. Where do these ones appear in your matrix on the right?
This one is just on the second diagonal.
Mm-hmm. And what do you have on the main diagonal?
And the others are all zero.
Oh, why didn't you use zeros? So there is decay on the left lower angle. There is one sub principal diagonal, which is ones, and all the rest is zeros. All the rest are zeros.
Yes. For example, we can easily calculate that the D power 2 is equal to the all zero here, and one here, here, and there are 2D power K here. And all others are zero. And also we can calculate that phi D of K just becomes back to the diagonal matrix dk and dk. So this is the construction of phi of this psi. And this psi just becomes an isomorphism of the centralizer and this matrix string. Okay, next.
Yeah. This psi is just a very explicit isomorphism. So you can transform the standard form of the element of the polynomial from the centralizer to a matrix form and vice versa. It's a very convenient way to represent an operator from the centralizer in different ways, in a matrix form, or in operator form, or in so-called vector form. Vector form, it doesn't appear here. Yeah, yes. The vector form is just identification of coefficients from this ring with this ring. So these rings are isomorphic. It's a natural isomorphism. Also not so trivial actually, but it also very explicit. And via this matrix, via this isomorphism psi, we can represent these operators from the centralizer in a very convenient way, suitable for many applications. I will see later.
What this vector means from H0 to from H0 to HK minus 1. What this vector means?
This vector is just here. This is here the elements in. For example, this is just an element here if it's written as this vector.
And also this vector corresponds to some elements from the right side, as Professor Jigoro said.
Yes. Do you remember, John, do you remember the isomorphism between K of A1 and sum of Ks?
Yes, it's just divided by the xk minus 1. It's just the sorry.
No, I mean there is an exact isomorphism which sends a sum which sends the polynomial in A1 to a vector of constants. Do you remember this? How to send the sum of AIs? Difficult to write.
AI of AI to this.
Yes.
To this.
Yes.
This is just multiplied by a Vandermonde matrix. If here we write operator, just we assume that it is homogeneous. This is I from 0 to k minus 1, and the vector form just the for example, we first written this coefficients here first as a vector ak minus 1. Then we multiply by a Vandermonde matrix here. V is the of the form 1 c k minus 1 c minus 1 and blah 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 is here k minus 1 square. Then we get the coefficients here in this place. Just for example, if we view this becomes h0 and hk minus 1, then this is all the coefficients here. This is our map.
Is this direct sum also ring or something?
Sorry?
Direct sum of rings is a ring. Don't worry.
Like pointwise, you mean?
Yes.
Yeah, pointwise.
Yes.
So this is kind of Gankel matrix, right?
Sorry?
This
kind of what?
Gankel matrix.
What is Duncan matrix? This.
Okay, it doesn't matter.
This is a Vandermonde matrix with all the.
Some resistance. Gankel.
Actually, this matrix has an additional condition that this any k times k submatrix is also of rank k. This is an additional condition for this. It's just some exercise in linear algebra.
Actually, of course, one can check that this is a ring isomorphism, but it's doable. It's not
ring from
not
what?
hard.
From such operators to this k-fold sum of k tilde, right?
Yes, because this is just a ring with very usual addition and pointwise multiplication.
Yeah,
and this is just a polynomial ring. And there, as isomorphic as rings, where this procedure, where this.
Since I don't remember the definition of A1 in any case, it's pretty
A1
technical.
is just a shift operator on the previous slide.
Yeah, I understand, but you really need to be in the topic to remember all the details. But yeah, I really believe it can be done.
Yeah.
So at a certain moment, these technicalities kind of accumulate, and you need to admit that something looks plausible, and that's all you can say.
Okay, then just remind of this. AI is written in this form, and the operators which commutes with partial Q squared can be written as the sum of this, and all the coefficients of the partial or the integral is just a linear combination of all AI from 0 to k minus 1, and all, A0 is just 1.
Mm-hmm.
Yeah, okay. Then next. If we want to parameterize all torsion-free shifts of rank 1 with the vanishing cohomology on a plane curve C given by the polynomial of weight degree nm, fxy is alpha x m plus blah blah blah. And here the terms of lower the c dots here is just means the terms of lower degree no more than the nm. And here alpha is not equal to 0, and nm are co-prime. We here just substitute y is equal to partial m, and x is the partial m minus add with blah 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 in the normal forms associated to this y. And this we can transfer this x into the matrix with unknown entries, and we give them the system of equations on the coefficients of rings entries by determining of the determining the affine algebraic set x of b prime. Here b prime is just the algebraic variety, the kxy multiplied by the equation f. And whose points parameterize all the such shifts. Now let's introduce the normalized normal form. For a given P in the centralizer partial Q, we can choose a normalization that's a special normalization and appropriate representatives in the matrix conjugation class. We will call such representatives as normalized operators. Here. Sorry. We will call commutative ring B prime the centralizer in the D1 sim tensor by K bar generated over K bar by operators P1 is equal to partial Q and P2 prime and PM prime. Here we just makes the P2 prime in the special form. We call it as a normalized normal form with respect to the orders. And so all the this conjugation is fixed. All the other terms of fixed here also fixed. We will call the coefficients of the operators pi prime as the coordinates in B prime, and we'll denote the xb prime as the corresponding affine algebraic sets determined by the relations on coefficients of the operators p I prime, and this is defined by the isomorphism class of the ring B. And maybe we can see more here. The relation just can be if here. First, we conjugate the SP1 of S comes to the partial Q square P1. Then we here choose a special S, because here there are many choices to have S. We can choose a special S just to make sure it is unique define P2 into the P2 prime. We can make some conditions in P2 just to make sure this S is unique and also unique here. So we fix the expression of S so that all the other terms now are also fixed under this choice of the under the choice of S. Then we know that these all terms are in the centralizer of centralizer, so that when we can use the formula before here to transfer them into the matrix. And after we if we, for example, we denote if we denote this, this will be say of phi of PM, just transfer, for example, this PM, maybe we can return as I to, we can transfer them into the matrix M Q K E of Q. Then this matrix must be of the determinant. Its determinant decides its relation between it and with partial Q square. Oh, so okay, this the determinant of this one. Just give a relation between PM with P1, so that they are, so that we know they are algebraically dependent. And this, the determinant is just, for example, defined by Fi. Then Fi is a relation to make them becomes zero. And all such Fi determines the affine algebraic sets here. Yeah, okay. Yeah, sorry. Next. Then we comes to the theorem. There is a one-to-one correspondence between the normalized normal form B prime with its spectral spectral B prime isomorphic to the C minus the infinite point P. And P here just P here is an infinite point. Because this C is from the project variety, and the P is here the infinite point. One here. Okay. And this is isomorphic to the conjugation class CP of F, modulated by the conjugation. And here F is the torsion-free shifts of rank 1 with vanishing cohomology. And C here is a projective curve. And P is a regular point. And this theorem indicates that the modular space of such shifts are affine open sets of the modular space of the semi-stable torsion-free shifts with fixed Hilbert polynomial on the curve. The geometric data CPF is just a part of the spectral data from the well-known classification of commutative subrings of the ordinary differential operators. Okay, there's another theorem here. Just let C0 be the affine spectral curve over C over X, and C is one-point compactification, and just C. Okay, just here is C is equal to C0 add with this point P, so-called one-point compactification. And we assume that OCC0 is isomorphic to the
sorry.
ring. Okay,
but
okay.
I'm sorry, but how do you algebraically define one-point compactification? Because well, it's pretty simple construction from the point of view of topology, but I have no idea how this is done algebraically.
Sorry, please again.
How do you define algebraically? You don't just need one-point compactification topological, I believe, but you really need one-point compactification in the world of algebraic curves. So how do you define one-point compactification in the world of algebraic curves? Can you explain?
Okay. C0 is in the affine variety.
I remember that it was written on another slide. Just list.
Okay, I didn't know.
On the other slide?
Yes, just list 1 or 2 slides and you will see.
Here? No.
Further. Here. Is written.
Here?
Yes.
So. Yes. Here, we define this C0 as the spectrum. The spectrum of B. This is
maximal spectrum, or primitive spectrum, or what? Or prime spectrum?
No, just algebraic spectrum.
What is it? I'm not familiar with spectrums.
This is endowed with the spectrum of.
So what I know, spectrum.
This is the constructed all the prime ideal in B and the.
This is prime spectrum.
Yes, this is ring space.
Because normally, because in topology, people consider maximal spectra.
No, here it is algebraic. So this prime spectrum.
Prime spectrum. So they consider prime spectrum. Then you do what? What is B tilde? What is BI?
BI is just takes the graded sum. B where we get the B tilde, and the BI is the homogeneous items in the graded ring.
But was B graded from the very beginning?
B is not graded. We can take all the homogeneous items of the same order, then we can define BI.
So you restore the grading, and that's what you call. So that's kind of projective spectrum. Just this. I thought it was called projectivization. Not one-point compactification, because geometrically it means that you actually embed your curve into projective space and then go to add the limits in this projective space. It doesn't. Why is it one point? I don't understand. If you take a curve in the projective plane,
no. It's a projectivization, of course. You're right, but in this part,
just 1 point.
Because it's specific of this construction. It's a specific situation of this construction of projectivization. It can be shown that that's indeed the 1-point compactification.
Very interesting.
It's some theorem. Yeah, it's not trivial.
So if you do this for multidimensional algebraic varieties, you don't get 1-point compactification.
Of course not. No. You will get some compactification, but not 1 point, of course.
No, so that's this kind of fluke. It's not 1-point compactification, it's projectivization. It's a fluke. Okay.
Yes, it's a projectivization, right, of a curve. But in this particular situation, this projectivization will be a 1 point.
So it's always for curves. It's always 1 point.
For curves, yes, okay. Just for curves, but not for higher dimensional varieties. But it's really a good question. But it is quite non-trivial.
Okay.
So it's a theorem you need to prove.
Okay, it should be. I think it should be known, very well known theorem, because people in algebraic geometry work with this all the time. I'm just ignorant of
in a sense, in a sense, Well, the construction of projectivization is known because it's a projective spectra of a graded ring, of a wreath ring. This is right, because this B tilde is called just a wreath ring. It's a usual construction.
Yeah.
But the property is that this particular projectivization of spectral curve of the ring of differential operator will be one-point compactification.
So it's just for this particular curve,
yes,
not for any curve.
Not any curve, but a curve constructed by the ring of commuting differential operators. Only.
That's really. Then it makes it. Then this statement is really non-trivial. I would really love to see how this is.
Yes.
But maybe next time.
Yes. It's non-trivial. This is correct. So in my book I explain this, but it's not a short.
Whose theorem is this?
Oh,
this is the Krishna classifications theorem.
Yeah, but well, who wrote first this theorem about 1 point? See, I think Mumford. So there are several, because Krichy were considered only, so to say, plane curves, and for plane curves it was actually more or less known like
geometry after all, not algebraist.
Yes. And maybe even Krichy was the first, but for plane curves, for arbitrary curves, that was formalized by Mumford. So Krichy, I think Krichy knew this too.
Plane curve? What do you mean plane curve?
I think also for non-plane curve, perhaps. But actually, Krichy considered just generic rings generated by two operators. So his curves were almost always plane curves.
What do you call? Sorry, what do you call?
I mean this curve, affine curve, is plane. It's contained in the plane, in the projective plane, but its compactification is not contained in the plane. That is the point.
Projective
For
plane?
example,
don't quite understand. Don't quite understand. So original curve is affine. Then you projectivize it and get 1 point compactification. The original curve belongs to some affine space. Do you mean that not all curves which you consider belong to two-dimensional affine space?
Of course not.
So Krichy considered only curves which lie within two-dimensional affine space.
Yes.
Okay.
Yes.
But the fact is true for all curves.
Yes.
Form. Yes. Okay. Mm-hmm.
And moreover, even for plane curves, this 1 point compactification is not plane. For example, the classical hyperelliptic curves are not plane curves.
What do you mean not plane? They are projective.
Yes, they are projective. I mean, they are not. They doesn't belong to a projective plane. That is the point.
But you don't understand this.
So you can consider.
I believe that what you do, you just take the affine plane, right? And then you add a third coordinate and consider the projective plane. So whatever to obtain by compactifying within projective plane is projective two-dimensional curve. I don't quite understand this distinction.
This is the point. When you make this compactification, it will not belong to the plane. And this is the point.
No, I can't understand.
The original plane.
It's not just the compactification in the real world.
Yes. It's not a compactification in a projective space, but it's
not completion in the sense of analytic topology. In the sense of analytic topology inside a projective plane. It's
yes,
not
because you can embed this.
So that's not interesting. Okay, that's not what would worry me.
That's because it can be embedded not only to projective plane, to higher projective space. So by that reason, this projectivization is not trivial.
Well, I actually don't understand all these distinctions in algebraic geometry, because people don't really live in algebraic varieties. People live with analytical varieties. So
well,
when
but the
to
situation is very
compactify
simple.
something, you do this in a naive way, just by adding limits of all sequences of points. So
Yes,
what do
yes,
you
but
by adding?
yes, but it is only no. Gosh, just if you compactify it in a given projective space, but you can embed it first into another projective space of higher dimension.
What's the purpose? What's the purpose of doing this? To get more
Because
points?
if you just take the projectivization in a plane, say, yeah, then the point which you will add at infinity will not be regular. But here in this project,
Well, the world is not perfect. It might not be regular. I'm not against this.
Yes, but here it is very important that this compactification is done with the help of a regular point. So this point which we add at infinity is regular, and it can be proven. So this is the main feature of this compactification. So it's but not only one point compactification, but one point compactification with the help of a regular. And it cannot be done in just in the plane. If your curve, say, was a plane curve, then.
But this point is not a point, I would say, because this point is not obtained by going to the limit.
It is not obtained by going to the limit in a given projective plane, but it is done going to the limit if you embed your affine curve to a higher dimensional projective. It depends on the embedding of your affine curve to some projective space. This is the answer.
If you choose another, you get another compactification.
Of course, there are many compactifications because there are many embeddings of a curve C minus P to different projective spaces. And in any projective space, you can make the natural.
And they are all one point.
Yes, but
that's very strange because I mean topologically, one point compactification is unique.
Just topologically, but the points you will add will not be regular in general case. This is a point.
Well, but
so in this particular situation, you can compactify your affine curve, say, also in the plane. But then the point you will add to the infinity will be not regular.
But then you just change parameters and get it regular, and that's all. Just
yes,
as you
yes, yes.
In differential geometry.
Yes. But this is very delicate point, because actually you get immediately that this singularity which you add just by usual compactification in the projective plane will be of very special type. It will be of cuspidal type. So this means that its desingularization is one-to-one correspondence, and this is an important.
Very nice, but that's geometrical after all. I can understand when you desingularize cuspidality, but I don't understand all this. Well, multiple points, choice of points, multiple choice of embeddings, and algebraic geometry. So sorry, just simple, maybe retarded guy who, well, for whom curve is a curve, a parameterized.
because it is not just a topology; it's an algebraic variety, and we have
That's
more.
what I say.
Yeah, more
There's
structure.
Nothing else, only topology.
Yes.
Okay, let's go on. Sorry for interrupting you, but
no. Thank you for your questions. I think Junho will be asked by other people about the same things.
I really love to see people not from algebraic geometry speaking about this, because it's still algebraic. I really would love to see people from the theory of apparatus, the theory of, I don't know, because when algebraists do this, they start speaking their own language, which is not common mathematical language. Let's put this way. Their one-point compactification is not one-point compactification we are used to.
Yes, we need to specify it, of course. So we can just understand it as a one-point compactification by a regular.
Yeah, okay.
But the question why it exists is non-trivial.
I understand. Well, let me say just a couple of words.
Yeah.
If when you compactify and you obtain just a cusp, then it's almost evident that by resolving this point, blowing up this point, you get a smooth curve. That's just it.
But it's not just a usual cusp. It can be a higher order cusp. So it's like,
doesn't matter how high this order. You just can just choose the parameters correctly. If it's fine.
Yes, but you need to resolve the singularity to show it. This is the point.
It shouldn't be logarithmical, probably. It shouldn't be exponential. But that's given for granted because you're not working with, well, non-algebraic curves. They always are polynomial. So the cusp will also be some finite order, maybe.
Yeah, but it's some claim. It should be proved. So
well, it's evident in this world, in this sense, in these words. Of course, it should be proved algebraically, but from point of view of naive guys, it's kind of okay. Well, I mean, I have just an image of a curve, one-dimensional, real curve with a cusp in one point, and well, it's just we all saw these examples of curves which project to a cusp when you look from them from the wrong angle, and that's more or less how this is done. And I believe
so for real curve,
yeah.
it's maybe a little bit easier because real curve is just something very.
Well, but it's not. Well, nobody has ever seen non-real curves. Let's put it this way. I cannot imagine a person who would, well, honestly tell me he had seen a two-dimensional curve in four-dimensional space. We are not four-dimensional beings, after all.
No, but here curves are just surfaces, Riemann surfaces, so they are.
I mean, yeah, I understand this, but I mean that whatever is true for real curves should be true for non-real curves. That's just a very simple. Okay. Naive. Okay, I'm not trying to, disparage whatever you've done with all this topic, but just trying to make this clear for people who are not into algebraic geometry like myself.
Yeah. It's a good question. It's good questions. Yeah, because this point is really very difficult. It's not so trivial to show all these details. Because
I mean, when Krishneva studied this point some 40 years ago, it all looked different. It all was much more geometric and maybe even analytic.
Because he was really more analytic than algebraic.
Yeah, that's precisely what I meant.
Yeah. He just considered Riemann surfaces.
Precisely what I mean.
Like hyperelliptic curve, because when we study hyperelliptic curve in differential geometry, we glue it from two sheets of C2. But yes, and more or less the same procedure was imagined by Krishneva and his. So he also constructed this one-point compactification for him was just a glued Riemann surface. And so the question is, what is easier? Yeah. So this question is, what is easier to you to glue Riemann surfaces or to take this algebraic?
It depends on your background.
Yes, of course.
Okay.
But to define this projectivization for arbitrary curve, not for just plain curve, I think it's easier to take this standard construction by Grotten.
Yeah.
Just three. You see three rows on the slides, and you get an
3 lines. Yeah.
But for Riemann surfaces, you need to say much more. Well.
Okay, let's postpone this argument to another place and time.
Yeah. Okay.
Okay. Then let's go back. Here I is just the ideal constructed by all the relations f1 to fk, the polynomials. This is a prime ideal with and the order of w1 is co-prime to all the other orders of wi. Then there exists normalized normal forms. B prime is isomorphic to the OCC0 with respect to the order sets of the generators. P1 is equal to partial Q and the others P prime. Here the orders of the P prime and Pi prime is just equal to the orders of W, and for all I greater than 1. And there is 1-to-1 correspondence between these close points to of the affine set XOCC0 and the isomorphism classes of the torsion-free rank 1 shifts F on C with vanishing cohomology. H0 and H1 becomes 0. And let's recall the Freischauer and Mulford classifications of the shifts. And there is 1-to-1 correspondence between the subalgebra of rank R to the spectral data CPF, the phi of rank R, modded by the conjugation. And if the B is rank 1, then there is only three spectral data C of CPF. And here B means the class of equivalent commutative elliptic subrings. Here, if B is similar to B prime, if it can be conjugated by a function f in D1 star. And here the similar is that they are up to the scale transformation, just makes the C x to the C inverse of x, and partial comes to the C of partial. And the CPF, the phi means the algebraic geometric spectral data of rank R. Let's introduce this. Here the rank of B is just defined by the greatest common divisor of all orders of the elements in B. Then the spectral data is constructed by the CPF Z phi, and C here is the integral projective curve on K, and P is the closed regular point, and F is a coherent torsion-free shift of rank R on C and with vanishing cohomology. And Z is the local coordinate at P. And here phi is just map all the shifts into the finite sum of the R times of sum in the functions, the power series of Z. This is a trivialization. It can be viewed as the OP model isomorphism. And here we just define the spectral B just is isomorphic to C minus P, and to
this we had just discussed. Just
yes,
go
okay.
further.
Okay. Now let's show Wallenberg's example. Here we assume that L is equal to partial square add with U, and P is equal to 4 partial 3 square add with 6 U partial and 3 U prime. Just U prime here, just the derivation of U. And here we written U as the infinite sum of the formal power series. And then L is of order 2 and P is of order 3. Then we know that L and P is commutative if and only if this equation satisfies. And we can hear it's easy to check that all the coefficients are uniquely defined by the equations step by step of the first three parameters u0, u1, and u2. And the spectral curve of these operators can be given by the these functions p squared is equal to this blah blah blah. And this is just the relation between p and l, and this polynomial determines the spectral curve. And here we can calculate the normal form of p with respect to l as this p prime. That's this. Also, so p prime is in the centralizer, so we can transform p prime into the matrix form here. So by fixing a equation of spectral curve, we get a one-dimensional fine algebraic set in A3 parameterizing torsion-free shifts with cohomology groups. Now we discuss the properties of Schur operators. The question is, what is the shape of Schur operators of S for harmonic differential operators of Q greater than 0? Here we can just answer that all homogeneous components of S are homogeneous canonical polynomial, and it satisfies the special condition AQ0 we will introduce later. And here if we here we denote the gamma L is x of partial L. It's good that this gamma L is of order 0, and the gamma L communicates with all elements AI. And here we denote Bn is just this, and here we can also view that the Bn is also of the order 0, and here denotes the Bj is equal to 0 for the minus degree. And here we denote the R greater than 0, the partial R, and if it's minus, then it is integral as before. Now we define the homogeneous canonical polynomial as the sum of in this form. And here we just all the f prime l I r and the coefficients g I j r are constant coefficients in k tilde. This representation is just unique, and this means that if h is equal to another h, then all the coefficients here should be equal to each other. And all HCP forms a monoid. This is closed set for the multiplication. And we call the elements is just as HCPC here, if it can be written as a finite sum of HCP. Here. Yeah. Or HCPC just form if K is fixed, then forms just a subring of D1C. We call it as HCPC of K. And suppose element in HCPC K, we can define stable degree of A and stable degree of B. The stable degree of A is just the possible gamma I, the maximum index of gamma I appears in H, and the stable degree of B is just the maximum index of B appears in the H. Here, just the stable degree is terms of L, A, and the maximal L here can appears, and the stable degree of B is just the maximum index can appear here. Okay, and then we say H doesn't contain AI if all the coefficients FLIR is equal to 0 for I greater than 0, and H doesn't contain Bj if the coefficients if the stable degree is equal to the minus infinity it's easy to see that here, if the doesn't contain AI, just means all the coefficients of AI just becomes 0. So there are only FLIR just can not be 0 if I is equal to 0. And if doesn't contain BJ, this means all the coefficients of BJ must be equal to 0. This is easy to understand. And here we should say that H, we need something more, not only contain BJ, but it's totally free of BJ. If H multiplied with D power P doesn't contain BJ. Here we can give the example that indeed doesn't contain BJ, but it's not totally free of BJ. It's very simple. Sorry. For example, the integral is a very simple operators. It doesn't contain BJ actually, because it is also already written as in the homogeneous canonical polynomial form, but it's not totally free of BJ, because if we multiply it with partial, then we'll get the terms contain B1, and so it's not. So it contains BJ. So H is not totally free of BJ. Here we define the condition AQK. We will say that an operator P doesn't satisfy the condition AQR if it is satisfying the condition that all the homogeneous term is HCP from HCP-CQ for any T. So this means that these terms can be maybe in the infinite sum of the HCP. And the second is that PT is not is totally, all the items are totally free of BJ for any T. And the stable degree of the terms P order P minus I is less than I greater than some with R for any I greater than 0. And the sigma P doesn't contain AQI, and the stable degree of the sigma P is equal to R. And we have the condition that suppose Q in D1 and order Q equal to Q, and P is satisfied the condition AQ0. And here, if we transfer P into the transfer Q into partial Q square, then the P prime comes to the normal form of Q respect to Q. Then we know that this P prime is satisfy the condition AQ0. Okay. Next. So we how we describe the differential operators in D1 sim, which might lies in the D1. We have the following statements. Then we can that if P, the first is just that if we want the operators P1 in P in D1 sim just lies in the D1, we call it as a formally elliptic differential operators, and it's equivalent to that for any P greater than 1, P satisfy the condition AP0 with that properties that all homogeneous components PJ doesn't contain AI. Also, here we just need not strong enough that for any P, just for one P, there is this one P that satisfies this condition that we can say is nice in D1. With help of this theorem, it's possible to give a new version of the classifications of the commutative rings of ordinary differential operators, which use only the old and the new versions of the Schur theory. We can roughly speaking that the B the classes of B is just one-to-one correspondence to the B prime and F. Here B prime just a normalized normal form, and F is lies in the centralizer. To expect this classification can be generalized to higher dimensions, and it will be helpful to prove the classification conjectures of the commuting differential operators.
Yeah, let me comment this this slide, because this was added by myself. It's a work in progress with Pavel Pichugin. It's another student who is here. I hope he soon will clarify this in very details. And then it's a work for the future to explain this classification higher dimensions. Okay, just continue.
Okay. The question is that what can we say about the normal forms for non-commutative operators?
So, look, I think the time is almost over. Just show, please, the new examples, because 1 year ago I make several talks about normal forms, but now we have something new, namely you computed examples of rank 2 normal forms.
Yeah.
Because
just how many slides in total did you have?
We have many, yeah, there are many slides, but because of this explicit examples, the last part of the work, which Jean calculated just recently, is a big example. He calculated all normal forms of all rank 2 spectral sheaves on an elliptic curve or its degeneration. And this example just shows that this theorem describing the modular space really fits well with known examples. The rank 2 sheaves were described in several works. So the history is written here. So the history is that Krichever and Novikov studied the pairs of differential operators of order 4 and 6, and they described a generic family. And this was a work which is really interesting. And by the way, Novikov, until the end of his life, always remember about his work, and probably he even thought that it was better than his famous work for which he got Fields Medal. But however, later Grunbaum, with the help of supercomputer, calculated all possible examples of these commuting operators of order 4 and 6. And then the history was that we have a classification theorem of commuting differential operators. And according to this theorem, any ring, in particular this one, generated by 2 operators of order 4 and 6, is classified by its spectral data. The spectral data consists of a curve, of a point, of a sheaf, and blah, blah, blah. And the most easy question, what is the geometric part? Well, the curve is an elliptic curve here, it's clear. The point is just a point at infinity. Now here, it's just the usual compactification in the projective plane. But what's about sheaf? For smooth sheaves, or for smooth curves, when the curve is really elliptic, not degenerated, but just elliptic, we have an old known ATIA classification of vector bundles on a curve. And Privyat and Wilson studied the question what are the spectral sheaves for a given pair of L4 and L6, say in terms of the coefficients of these operators. Coefficients are here some series V of X, R of X, and W of X. And then
polynomials of functions. These R of X, W of X, are the polynomials of functions?
Just functions,
So they're not polynomials. They're analytic
No, there can be polynomials too. And these are the first, and the polynomial case was studied first by Dix-Millet. So actually the first example was constructed by Dix-Millet, but it was just example. Krichever and Novikov describe a generic family. They describe this coefficient explicitly in terms of various trust P functions, but again in generic position. And absolutely all commuting operators was described by Grunbaum with the help of supercomputer of that time. This is the history. Then Privyat and Wilson described the spectral sheaves for a given pair when the spectral curve is smooth, so when it is elliptic. And for singular case, they were described only in our work with Igor Bourbon, because in singular case, the zoo of this torsion-free rank 2 shifts becomes bigger. And in fact, as I learned from Igor Bourbon, if you consider rank R torsion-free shifts or just Caspidal curve, then it appears that the task, the problem of description of all such torsion-free shifts is representation theoretically wild. So it's the task of classifying all such torsion-free shifts is equivalent to classifying all representations of free algebra. But for concrete rank, it's possible to describe them. And in particular for rank 2, it was done before in the work by Bourbon and his teacher Drost and other guys from representation theory. And we just finalized this work of Privat and Wilson in that sense that we described all spectral shifts corresponding to a given pair L4 and L6 in terms of their coefficients, if the curve is singular. And now, so this situation is very well studied. And to check, so to prove that, to show that our theorem, that our new theorem about parametrization of torsion-free shifts with the help of normal forms is correct, we decided to calculate another really non-trivial example and calculate on normal forms of these rank 2 shifts. And this work was completed just recently, and we get really very nice list of normal forms which describe really all torsion-free rank 2 shifts. And this example shows that really our description fits well with known description of torsion-free rank 2 shifts. And now, John, you can just quickly show the table without any detail.
Do I have to explain this?
Well, no, maybe just for notation.
No.
Yeah.
Oh, okay. Well, just give a quick review of this. We here just assume that just denotes the category semi-x category of semi-stable coherent shifts of x of slope 1, and denote S as a unique run object of semi-6 which is not locally free. And A is the rank 2 RTR shifts, and when x is singular, and denotes Q is its smooth point, and then BQ is decomposable rank 2 locally free shifts from semi-x, and if x is Caspidal, then U denotes the unique indecomposable and not locally free objects from semi-6 of semi-x of rank 2, and when x is nodal, there are two subjects, U plus and U minus. Let's now show the normal forms respect to the different shifts. And here, in the case that F is isomorphic to S at with S here, and this is in the case of X is singular and the Rx is equal to 0. We call this as a self-adjoint case, and here Wx is constant. The normal forms H must be equal to d power 6, and matrix form should be in the form of this. And this is in the shift is equal to isomorphic to BQ case. Here there are two possibilities. H1 is equal to this, and H2 is equal to this, and this are their matrix form. So there are two possible forms. We have this proposition that if B and B prime are two computed sovereigns, but they have the same shift, then there exists an operator that from the centralizer can transform them together. And here we can calculate this. For example, here T just should be in the form of this one, and the matrix form T here just can conjugate the matrix form of H1 and H2 to be equal. And this is in the case of the OQ1 plus OQ2 case. Here, there are also two possibilities in the self-adjoint case, and here we can see that their matrix form are also similar by the conjugations of T1 hat here. And in non-self-adjoint case, there are also two possibilities here, and H3 in this form and H4 in this form. They also can be conjugated by the matrix. This is the matrix form of H3, and this matrix form of H4, and they can be conjugated by the matrix T2 tilde here in the form of this 4x4 matrix. And in the A tensor OQ case, there are also two possibilities in the self-adjoint case, and they can also be conjugated by this matrix. And in non-self-adjoint case, there are two possibilities, H3 and H4 in the forms of this, H3 in the form of this, and H4 in the form of this. They can be also conjugated by the matrix of tilde 2, tilde T of 2. And here there are there are shifts of if OQ plus OQ, the matrix form is like this, and the non-self-adjoint case, the matrix form is like this. And finally, if F is isomorphic to U case, this can only happen in the non-self-adjoint case. And this two matrices also can be conjugated by the matrix here. So these are all examples, all possibilities of the rank 2 case. And that's all.
Just in the end, it was just kind of barrage of very, very hard to understand matrices, very large matrices with notation which probably erased back to something we were supposed to learn, but definitely it's too hard to learn something in such speed. Can you just give me just one question? Did you manage to get a new example of computing partial differential operators in this situation?
And so here, the situation here we study just ordinary differential operators.
In new examples of ordinary differential operators, not ordinary commuting differential operators.
What for new example? No. That's no. To get new examples of ordinary differential operators, we need commuting. We need not only the normal form. So the normal form can be always calculated. That is true. So the statement is that it's possible to calculate normal form for any spectral data, and quite explicitly. And the list of these normal forms up to certain conjugation will give a list of torsion-free shift up to isomorphism. But to restore from a normal form, say if we have a matrix, for example, H4 hat here, if you have a matrix, how to restore the differential operator is a different task. It's not, well, sometimes it's possible if the rank is 1, because in that case, we know that the coefficients of operators are given by the Ricciverse formula via theta functions, and in principle, we can restore them. For rank R case, it's much more difficult because we can get some transcendental functions. So we can only calculate these coefficients as series. And sometimes under some suitable condition, we can probably restore some rational coefficients or polynomial coefficients, but we need some additional information for that. But
you see, I'm again trying to, well, look at this from a point of view of a very simple-minded person. A simple-minded person will probably, well, just ignore what torsion-free sheaves are.
Yes.
probably also we will forget very quickly what are normal forms, especially normalized normal forms.
Yeah.
You will immediately forget all the notation, K1, 2, D, I, G0, G1, and so on. All these barrage of formulas, it will vanish, it will evaporate immediately from any reasonable person's brain. Maybe some, genius will keep it in mind, but I'm not genius. But what every normal mathematician understands is pairs of commuting differential operators. And whoever has ever tried to find commuting differential operators knows it's quite a rare thing. So if you want to justify all this very hard work to an average person, not to a specialist, not an expert in algebraic geometry, in the theory, in Kirchhoff's theory, and so on, but an average person, an example of something which you obtain, which would be understandable to anybody, I think is really very important. And it's kind of recommendation.
Yeah.
If not, if you, I'm not trying to say that it's actually something bad, but if you can provide it, it would make your not just talk but the whole work much more popular with average people like me.
Yes, of course. So the answer, the right answer is here that I expect to apply all the things to construct commuting partial differential operators in high dimension, because in one-dimensional situation, just for ordinary differential operators, the theory is already very well known, and to construct new examples, say, of high rank, it's a kind of very specific task. Well, you can. So first of all, there are already known a lot of examples. To construct new, well, it's not clear why it's so interesting. To construct a 4 rank 1 commuting differential operators, it's more or less everything is known because we have a Kirchhoff formula. But what is not known, what happens in higher dimensions? In higher dimensions, commutative subrings of partial differential operators are much less known. There are many works on representation theory, many guys who try to construct certain quantum integrable systems like Kolazhar-Moser systems and their deformations. Misha-Fegin, Veselov.
They're just examples, they would say.
Yeah.
And they totally different from what you do here.
Yes, exactly. But now we have another point of view on that. So this is a classification theory which can be extended to high dimension. And in high dimension, the problem is to find an appropriate geometric spectral data, because in dimension 1, the modulus space of such torsion-free sheets is always non-empty. But in dimension 2 and higher, the modulus space of such torsion-free sheets, such spectral sheets, can be empty. And the first question, how to find surfaces with non-empty modulus space. So with the help of this technique of novel forms, this question can be resolved.
I see.
Second question, if you know the surface, how to find all examples, even in rank 1. So rank 1 case in dimension 1 is very well known because we have Kirchhoff formula. Rank 1 case in higher dimensions is not known at all because there are no Kirchhoff formula. There are only some examples. But for rank 1, this technique works perfectly because we know that it's some kind of algebraic function. And we were able, say, with Igor Bourbon and other work, to construct new deformations of Kolazhar-Moser systems, which are not differential operators, but some mixture of differential and difference. And so, and this is the first step. So this work about description of modulus space is the first step to do the same in, say, dimension 2 and then in dimension 2, we can apply this technique to construct new examples. And this is so to say the program application.
Okay, I see. So it's a very nice program, and I hope it will work. As for Moza, I think I've seen some people do this differential difference operators, Dunkel operators, and so on. I think Misha Fagin was talking about this a few years ago in the context of Moza. Okay.
Not only Misha Fagin, you skipped this workshop in BIMSA with all half of participants spoken about quantum integrable systems. But in fact, I expect that also some metrics quantum integral systems constructed by many people, say by Sasha Arlov and by other guys, and also algebras of shift arguments. So I mean, I expect that even universal and Melton algebras can be probably embedded to this ring D and head C. And then it's interesting to study these algebras from that point of view.
Well, but these algebras are quite complicated, and there are like n-square variables, and even if you have one variable, you have such complications. I'm really afraid of looking into this. Because when you have n-square variables, n-square partial derivatives, and you have all sorts. I really don't think this is the best way to think about partial differential operators on coadjoint orbits. Okay, that's a big discussion.
Surely it's just.
Sorry, too late. So let's thank the speaker. And that was our last talk this semester. We'll resume, I hope so, in February. If you have anything you would like to talk about, or if you know anybody who would love to make a talk in our seminar, just let me know. We'll try to arrange this talk. Thank you.
Okay, thank you.
Yeah, okay. Thank you.
Thank you.
For me the opportunities to make a talk.
Yeah. Don't be shy. It was a nice talk, just it's kind of Russian style of making talks.
Thank you for your questions.
I remember when I tried to make a talk at Novikov's seminar, I could barely speak a few lines. I tried to give some motivation, and then Novikov started to ask about this topic, which was not actually a topic of my talk. It was motivation. I had nothing to say. I hope my talk, my explications today were a bit more close to the topic. Okay.
So now, are you all in Beijing?
Yes.
Shanghai.
We are in Shanghai. Jonko is in Beijing, and other guys in Moscow.
I see.
Yeah, Isushi, I'll contact you because I really need your help with my exam. Can you please? Okay, but that will be next Thursday. I'll be on my way to Moscow, and I'll ask you to start this exam. I'll come and pick up the test works. Okay.
I see. Yes, fine.
Okay, thanks. I sent you the materials, everything by Wednesday.
Okay.
Okay. And bye.
Bye.
Goodbye.
Bye.